So shall we start, sir?
Once again, sir.
Yes.
Once again.
Yes, sir.
Sir, okay, sir. We can start, sir.
Okay, sir. Fine. Good evening and a warm welcome to everyone present here. Our esteemed speaker, respected faculty members, and enthusiastic participants joining us from different parts of the world. It gives me a great pleasure to greet you all on behalf of MEASI Institute of Information Technology as we gather for day 3 of our online international faculty development program on the theme Emerging Frontiers in Generative AI and Deep Learning from Vision to Language. We are delighted to have such a vibrant and diverse audience with us today. To begin this academic session with grace and tranquility, I invite Mr. A.K. Mohammad Gauss, Assistant Professor, to recite the Kirat and bless this gathering with spiritual harmony. Sir, kindly please, sir.
Yes, sir. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم أرأيت الذي يكذب بالدين فذلك الذي يدعو اليتيم ولا يهد على طعام المسكين فويل للمصلين الذين هم عن صلاتهم ساهون الذين هم يراءون ويمنعون الماعون. صدق الله العظيم. Thank you, sir.
Thank you, sir, for a soulful recitation. To extend heartfelt greetings and to introduce today's distinguished speaker, I now call upon Mr. G. Veeranageshwaran, Assistant Professor, to deliver the welcome address, followed by a brief introduction about our resource person, Dr. M. Suresh Anand. Sir, kindly proceed, sir.
Yes, sir. Yes, sir. Good evening to everyone present here. It is my great privilege to welcome our distinguished resource person, Dr. M. Suresh Anand, Assistant Professor in the Department of Computing Technology at SRM Institute of Science and Technology, Katangalthur. Dr. Suresh Anand comes with a strong academic foundation. He completed his Bachelor of Engineering in Computer Science and Engineering in 2002, followed by a Master of Technology in 2007. Demonstrating remarkable dedication towards the research, he earned his Doctor of Philosophy in Information and Communication Engineering from Anna University. With an impressive 20 years of teaching experience, Dr. Suresh Anand has made significant contributions to academic and research. He has published more than 50 research papers in UGC approved and Scopus indexed journals and conferences. His innovative outlook is reflected in his 13 filed Indian patents and as well as several granted Indian design patents. Additionally, he has contributed to knowledge dissemination through authored books and book chapters. His research expertise spans several cutting-edge domains, including image processing, computer vision, machine learning, human-computer interaction, deep learning. Dr. Suresh Anand is also an active member of professional bodies such as ISTE, ACM, IEEE, and CSI, demonstrating his continuous engagement with global academic and technological communities. We are truly honored to have him with us today, and we look forward to gaining a valuable insights from his expertise. Once again, I welcome you, sir, and also I welcome our director, HOD, all our staff members, and the participants. Thank you.
Thank you, sir, for your warm words of welcome and the insightful introduction. Now, we are privileged to move into the core part of today's program. We feel honored to have Dr. M. Suresh Anand with us to lead the today's session. Sir, we request you to bring your presentation.
Thank you for the introduction. Good evening to everyone. So I'm Dr. Suresh Anand from SRM University, Katangoluthu. So actually, I'm very much excited and delighted to give a talk on this GenAI models for image and video recognition analysis. Actually, in recent years, AI has moved beyond just creating text and images. So it becomes fundamentally a fundamental pillar of the modern computer vision. So these models do not just generate images. So they learn the data structure and with the probability distribution of data, which enables the systems to understand the data. Data in the sense image, video, text, audio, anything. So it is more like a human-like contextual way. It is going to read, understand, and generate the text, images, and whatever. And in today's session, we will explore the basics, the fundamentals, and intuition behind the AI generative models, and how these models are recognize the image and video, especially, and the types or variations in these models, and some real-world applications. So in this session, we'll be having the theoretical part and as well as some real-world applications along with the demonstration. And finally, we'll be having a small quiz on that. And as I said, the generative models or generative AI models. So we are thinking about the ChatGPT, Gemini, uh, two things, right? So beyond that, there are many Gen AI models are available, like Claude, Mistral. So these are all some developing Gen AI models. So apart from these models, the ChatGPT, Gemini are the top notch. So that is what we know. We've been using that, right? I hope this session gives you a new insight on GenAI models and image and video recognition. So that is what we're going to see now. And let's start how it is happening. So the agenda of today's session is so the basics or introduction about the GenAI models and the various types in that, and GenAI models for images and as well as the videos. And most of the cases, the image GenAI models is slightly transferred to the video recognition and analysis. So most of the same. And finally, we are having this. So coming to the introduction, the definition, what is GenAI model? So GenAI model is nothing but it's a machine learning algorithm or model. As I already told you, so it learns the structure, underlying pattern of data. So how the data are interlinked, how the data are connected to each other, related to each other. So with that, so the GenAI models generate new realistic data similar to the original, but it's not original. So we'll be generating hyper realistic data, hyper realistic images, as well as the videos, even text also. And GenAI models are algorithms. Another way I can say GenAI models are algorithms that learn the probability function among the data and use that knowledge to create a new samples that resembles the original data set. So another way of what is GenAI model. And one more way, so GenAI models learn the probability distribution, that is P of X comma Y. So people know. So as and when we are talking about the machine learning, AI, machine learning, deep learning, so you have to think about the statistical probability mathematics in behind. So we need a strong mathematics, statistical knowledge to explore the machine learning and deep learning models. In that, so the P of X comma Y is a kind of a joint and as well as the conditional distribution of the data. So with that, we can, the GenAI models can generate new sample of data or new images, new text, new videos, and even more. So it performs unsupervised learning, and the model is hidden. So this GenAI models are people will call this as an unsupervised model. Actually, the GenAI models are self-supervised model. So it is studying the data, it is generating new data, and it is going to be getting the feedback from itself. It's not from the human. Generally, in the machine learning, we used to give the feedback. As a human, we have to give the feedback. But in GenAI model, so the machine itself takes the feedback from the machine. So it doesn't take from the human. So that is what self-supervised learning or unsupervised learning. Initially unsupervised learning, and later on it is going to be self-supervised learning. So that is what the GenAI model is about. And this is what I told you. Right? So what the generative models can generate. So as I already told you, so it can generate all kinds of images, text, videos, and even audio, sometimes 3D models, or even in sometimes you can generate a new data set which is synthetic data set for research purposes. So text, image, audio, video, 3D models, and data samples, random data samples for the research purposes. So these are all the things. All these are all synthetic, not original. It is closer to the original. So that is what this GenAI model are generating, a different kind of data. And GenAI models learn, already I told you, right? So GenAI models learn the underlying data distribution and can synthesize new samples. So the word synthesis, we know it very well. It is going to be creating artificially, or it is fabricated. So that synthesized samples could be synthesized images, synthesized video, and even motion sequences and text or random data too. So more than a generation, so the GenAI models have become more powerful tool for representation learning. So representation learning means the model can understand the data on itself. So it is going to self-learning. That is what called as representation learning. So no need to feed say what it is. So it is going to read the data on its own and understand what is the data is about. That is what called as representation learning. And recognition, as you know very well, so by seeing the pattern, so it is recognize what kind of data it is or what kind of feature it is based on the features. And reasoning, so based on the data, it can reason the data. So what is the meaningful insight from the data? That is what reasoning. And as well as the multimodal understanding in the computer vision. Multimodal means, for example, if you feed a video file to the GenAI model, it can understand frame by frame as a video. It can understand the text in that. It can detect the object in that. It can detect and identify who is the speaker and what he speaks and generate the text from the speech and all kinds of. The modality is multi. So it is reading the image, reading the objects in the image, and reading the frame by frame video, and reading the who is reading from who is there in the video. So everything. So in all modalities, it can understand the video. So that is what the multimodal understanding. So more than a generation. So it's a GenAI is a powerful tool nowadays for self-learning, recognition, reasoning, and as well as the multimodal understanding in computer vision. And as a whole, I can say the GenAI model performs recognition, generation, analysis all together. So it can recognize what it is. It can generate based on the previous frame or previous data or previous text or previous image, and based on the input, and as well as it is doing some analysis, which may be giving us a useful insight about the data. So that is what about the introduction to GenAI model. In simple word, the GenAI models are machine learning algorithms or models which can generate the data which is closer to reality or closer to the original data. That is what the GenAI model. And now we'll see some types of GenAI models. So there are some, these are popular types I categorized in this way. So the first one is GANs, the Generative Adversarial Network. So popular GenAI model. And the variational autoencoders, it is a derived or enhanced version of the autoencoders. And autoregressive models, diffusion models, and flow-based model. And finally, this is my one type, that is a hybrid model. So you can hybrid the generative and the discriminative model. Generative model is creating new data, creating new image, new video, or whatever it is. Whereas discriminative model is, it is a kind of classifier, or it is giving, if you give the input, it is saying what class it is. So that's what matching kind of thing. So based on the feature, it can say what kind of data it is. So that's what the plain old model, just a discriminative model. And generative model is purely creating new data. So the matching model and as well as the generative model can be combined together. And one more option is there. You can combine any of this GAN, VAN, VAE, autoregressive, diffusion models, flow-based model together. That's also possible. That's also a hybrid GenAI models. So according to my perception, I given these are all some popular GenAI model. So we'll explore one by one, not too much mathematically, but we will discuss how it is working and the use cases and the types of each. So that is what we'll be seeing. let's move on to the GAN. So GAN is a generative adversarial network. So based on that definition, based on the name itself, I can say, so it is derived from the neural network. So it's a kind of neural network which can generate new data. The data can be generated in a kind of competitive game. For example, we're having two models here. So one model is generating the fake images or fake data. The other model is trying to find out whether it is a fake or real. So that two model, that is a game kind of competitive game model, which is going to be used for generating new images. So that is what the GANs or adversarial. Adversarial means one is giving the fake one. The other one is going to be detecting which is fake or real. So the first one is called as generator. So two entities are there in GAN. So generator is creating the fake or duplicate, fake data. Wait a minute. Yeah, sorry. And second is discriminator. So which is finding whether the supplied or given input is fake or real. So that is what the two model. Then the first model, generator, generates the fake data. And the second model, discriminator, finding whether it is so the discriminator is a kind of ML algorithm which is analyzing the data with the original data as well as the synthetic data. By learning the patterns, it knows, it is saying that whether it is fake or original. So that is what the discriminator. So with the diagram, I think we'll, yeah. You can see this diagram. So we are having two components here. First one is generator, second one is discriminator. So generator generates or produces the fake. So you can see over here. So in the bottom, generator produces the fake images or fake data or fake video or whatever it is. So here the discriminator is actually it is having a knowledge of how the original data look like. So with the real samples, it also learns how the original data will look like. So the goal of generator is trying to generate the data as much as closer to the original. And the goal of discriminator is going to be detecting whether the data is original or fake. So how it knows? So discriminator already have a knowledge about how the original data look like. So from the real samples, it analyzes, studies, and it has its own knowledge base. So with the discriminator, so discriminator model is getting the input both from the real sample as well as from the generator. So always generator is creating the fake. So finally, so if the discriminator not able to find the duplicate or fake one from the generator, that is the success of the GAN model. Are you getting? So if the generator is generated some fake data, fake image, which is applied to the discriminator, if the discriminator is not able to find it is fake, so that means it is closer to reality or closer to the original or real. So in that case, discriminator wins. Generator wins, discriminator loses. So that this is how the two-player adversarial games happening in GAN. So I'm not diving deep in mathematical statistical parameter. I'm just saying how it is happening. So GAN is a two-player adversarial game. So which is generator generates the fake and discriminator finds whether it's a fake or original. So that is what the GAN actually working. So let's so I already told it. So the objective. So the objective generator objective is producing the as much as fake data. So where the discriminator believes that it is a original. That is what the generator objective. Generator is actually generating fake, right? So it has to generate the fake images or fake data. So the goal of generator is it has to fool the discriminator. It has to win the discriminator, or discriminator has to make a mistake that it is the original. So that is what the goal of a generator. So it has to create as much as closer to the real data. That is what the discriminator objective. So coming to the generator objective. So coming to discriminator objective. So it has to maximize the probability of correctly identifying the fake or original, or fake or real. So discriminator always trying to find out whether it is fake or original. So that is if the generator wins, so we are getting the hyper-realistic images. If the discriminator wins, so the generator fails actually. So that's what the two adversarial game. So here in some case, here we are having backpropagation also, which generally used to optimize the model. So that is what the GAN is actually working, generator and discriminator model. let's get into that some types or the variations in the GAN. So GAN, so there are several implementations or several way of implementing the GAN models, the generative adversarial network. So the first one is a deep convolution. We're applying more convolution layers in the adversarial network. So that is what, so since it is based on the neural network, so deep convolution GAN is one type. And the second one is pixel to pixel, pix to pix, or we can call that as a cycle GAN. So here it is working like image to image matching. So we will be matching pixel to pixel, or frame to frame, or image to image exactly matched, and it is translated. So that is what the pix to pix cycle GAN. And the third type is style GAN series. So style GAN series is actually designed for detecting the generating the human faces. So it is this SOTA, the state of the art for human face generation. And the last one and the fourth one is video GAN, so or Moho GAN. So by the name itself, it is generating hyper realistic videos or temporal video. Temporal means at time series video frames or images, which is going to be considered as a video. So this video GAN is used for temporal video generation, temporal image frame conversion in counter to the video. That's what the video GAN. So these are some implementation or variants or types in the generative adversarial network. So it is based on the two-player game, that is generator and discriminator. Generator generates a fake data. Discriminator try to find out whether it is fake or original. So that is what the variants. So these are all some applications of GAN in terms of the recognition. So in augmenting training data, so irrespective of the image pose, say it may be in different pose, or we may not get the full image, and it may have a low lighting, different lighting conditions. Even though in that condition we can train the data with the augmentation. So that is one area where it can apply in the recognition. And second one is refining the segmentation. So segmentation means dividing the images into based on the region of interest. So that is what. So that can do it better by using GAN. And domain adaptation. Adaptation means we can generate the data as much as closer to the real. For example, if you supply an image to the GAN model, it can add some features to the photo or image. For example, if you supply a image of the person, a photograph of the person, we can add a different hairstyle, or adding the spectacles or coolers, or changing the emotions of the person who is in the photograph. That is what closer to the reality, but it's synthetic. That is what domain adaptation. And generating the rare event samples. So some samples are not happening, which is actually needed for research purposes. In those scenarios, with the past data, we can generate a similar kind of thing, which is closer to the reality. That is what this one. And also it helps in recognition networks and generalized better. So these are some recognition applications where GANs can play strongly. And for analysis, video frame interpolation. Interpolation means generating a new frame. What would be the next frame? So that is what the interpolation, or generating the missed frame. And that is one way. And the second one is image inpainting. Image inpainting means we can correct the damaged images. You might have seen in your social media, if you supply the old image, it is correcting and coloring and filling the missed area. So reconstructing or filling missing or damaged images, that is what image inpainting. One more thing is that image outpainting is there. So the ulta of this one, this image outpainting. So inpainting is actually filling the missed data in an image. And generating super resolution images. So GAN is one of the best model for generating hyper resolution images, which is SR GAN and ESR GAN are the variations in that GAN. SR GAN is super resolution GAN, and the ESR is enhanced super resolution GAN. So this is especially for generating high resolution images from the normal resolution or the low, or it can generate the hyper realistic high resolution images. And colorization. So if you supply the black and white image, we can add the colors to them, and shadow removal from the image. So these are all some applications where GAN doing the image and the video analysis. So let's see some examples of GAN as a video. So you can see over here the data accommodation. So here, if you supply the photo, we can add emotions to the person, which is not actually true or real, but we can make it. That is one application. And second application is these photographs are not real actually. So these are all generated by the GAN, which is not actually real, or which people who do not exist actually. That is what this is one way. And this example, we can generate the image to image. So you can see over here. So from the Google map to the satellite image to the Google map, and from the image to the wireframe, or from black and white to color, or in different way we can generate the images. And see, in this example, if you supply the prompt to the GenAI models, which can generate the image. So these are some samples where you can give the prompt to the GenAI model, which generate a flowers or anything which is not actually really exist. And in this example, you can see which is editing the photograph. So adding the features like adding different hair color, hairstyle, smiling, and different changing the faces too. So we can change the features of the real image if you supply the photograph. This is another example. And coming to this one, photo blending. So we will be having two different images we can blend together. That is what called as photo blending. So it is done beautifully by the GAN. And this one you can see face swapping happening in social media. So swapping the faces of the two person. So of course it is having some ethical consideration. So this is one example is happening. And changing the features, swapping the faces from one to other. And video prediction. So this is one of the best application where we can generate the new frame. I mean, we can predict the new frame. So from the past frame. So that is what actually possible. So that is possible with the GAN. Yeah. Yeah, predicting the future frames in the video is impossible with the GAN. And last one is domain adaptation. So we can change the data to the in another way by adapting some changes like camera angles, lightings, even adding smiles, I mean emotions. So all this kind of thing can be converted. So that is one application. So that's it about the various applications, real world applications of the GAN. So let's dive into the tools available for implementing the GAN. So actually some libraries are there for implementing the GAN. Libraries or frameworks are available. So one such library is TF-GAN. So TF-GAN is TensorFlow GAN. So it provides a component for implementing GAN operations. And second framework or library is PyTorch GAN. So PyTorch GAN, it provides some basic building block for generating GAN architecture. And Studio GAN is a library for conditional and unconditional image generation. And HyperGAN, another way, it provides API for generating user interface for GAN applications. These are some libraries and frameworks for implementing GAN. And one interactive educational tool is there in this website. So where you can practice the how the GAN is actually, you can add your own data, and where you can add layers and customize layers, tune the parameters, and you can test your data with the GAN. So this is actually available. You can check it out. So poloclub.github. So in this domain, you can check it out. So that is about the GAN. So GAN is actually generative adversarial network. So it is a kind of two-player adversarial game. generator is generating the fake data, discriminator is detecting whether it is a fake or original. That is what the basic of the generative adversarial network based on the neural networks. So let's move on to the second type, which is variational autoencoders. So VAE, so actually it is derived or slightly changed from the autoencoders. So autoencoders, again, it is a neural network. So it compresses the data to the lower dimension, and then you can reconstruct it to the closer to the original. So that's what autoencoders. So the compressing the data to the lower dimension is actually reducing the dimension. So we can call that as a dimensionality reduction. So many techniques are available in machine learning for reducing the dimension. So this is one way. So in this this VAE is actually a self-supervised generative models generate a new data in the form of variations in the input data they trained. So it just adjusts the variation on input data trained on, and it is reducing the dimension. And from the reduced dimension, it is going to generate the data or reconstruct the data as it is closer to the original. So this is what the basic of the autoencoders and variational autoencoders. This way, variational autoencoders compresses the data into probability distribution, then samples it and reconstruct the data, right? So which is learning to generate a new versions to the similar to the original or closer to the original. So it is a probabilistic model, learns the data in a latent representation of data using an encoder-decoder structure. So as and when the name suggests autoencoders, we are having two components here, encoder and decoder. So the encoder is going to be converting data from data to the higher dimension to the lower dimension, just actually dimensional reduction. And the decoder is going to be reconstructing the data from the lower dimension to the higher dimension, or reconstruct the data from the latent space to the data which is closer to the original. So that is what the VAE. So the architecture is having three components. One is encoder, bottleneck, and the decoder. Encoder is where the autoencoders are converting your data into vectors. So that is what called as encoder. Or we can convert the data into embeddings. That is what encoder. And the bottleneck is where we are having all the vectors. So the converted dimensionality reduced vectors are called latent space. So they're in the latent space. That is what called as bottleneck. It is a fully compressed low dimensional embedding of the input data. So from the embedded low dimensional input data, so the decoder is going to be constructed. So from a latent space where we are having vectors. So those vectors are the from the input data by applying a function. The data is actually embedded to the latent space. So from the latent space vectors, we are the decoder is reconstructing the images or data. That is what actually the VAE works. Let's see the diagram. We'll understand easily. Yeah, this diagram. So where you can your input data is X is actually. So you are having your probabilistic encoder which converts your input data into vectors. So those kept in a latent space. Or I can say this Z is actually reduced dimension of X by this function, and it is represented as a vectors in a latent space. Okay, so we can call that as a bottleneck. You can see this diagram. So this is the original input data. By applying the probabilistic function, so this data is converted into the vectors. So we call that as a bottleneck or latent space. So from the latent space or bottleneck, the decoder is reconstructing the data. So this is the reconstructed data, original data, latent space. So that is what given over here. So the input data is converted to the latent vectors in a bottleneck. So it is a compressed low dimensional representation of the input actually. So the decoder, it is having the reverse of this one. So it is going to generate or reconstruct the data from the latent space. So this is how the variational autoencoders works. So I'm not getting deeper in this mathematics. This is the architecture, how the VAE is actually working. Basically, neural network. And coming to the so why we are using the so it is compressed representation of data. So the VAE is actually reducing the dimension. So the important features are kept preserved, and the noise are ignored. Unwanted noises are data are ignored. So in a lower dimensional embedding, so with that we can, which is useful for downstream stuff, which can be easy to handle. And remember, so this is not made for classification. So the lower dimensional embeddings are used to understand the data, and later it is used to reconstruct the original data, not original, similar to the original or closer to the original. So that is what the VAE actually. So these are all some variations or types of VAE, or different types of implementations of VAE, that is variational autoencoders. The first one is beta VAE. So beta VAE is actually adding the weight beta. The people who is in machine learning know what is beta. So beta is a weightage to the functions, and the KL divergence is where it is limiting the errors. So with that, we can add the weightage where it is going to be adjusting the errors. That is for the beta VAE. And second one is CVAE, so the conditional variational autoencoders. So it adds the conditions, extra conditions like labels, attributes to the encoder and decoder. So additional information is added as the condition. That is what conditional VAE. And the third one is hybrid, the VAE and GAN. So VAE is the one generative model, GAN also another generative model. So we can combine these two models. So we can leverage the strength of both the components. That is what the VAE meaning hybrid. And the fourth one is vector quantized variational autoencoders. So they converts the continuous latent space into discrete codebook vectors. So already we are converting your input data into the vectors in the latent space. So that is going to be into discrete codebook vector. So another level of embedding. That is what vector quantized VAE. And another one is a hierarchical VAE. So where we are using different layers in the latent variables. So in the diagram, I shown only one layer, right? So like this, we'll be having several layers of neural networks and several layers of latent variable. That is what called as hierarchical variational autoencoder. So these are all some popular type, and we can have different implementation use the different types of VAE. So I given the most popular variational autoencoder implementations. So let's move on to the applications or how the VAEs are placed in recognition and analysis. So the first one is the latent features for classification, and it is the hidden dimensionality reduced features are easy for can be used for classification, and the most widely used application by VAE is actually anomaly detection. So it finds the difference between the original and the fake, or it is used to find the difference between if there is any abnormalities in the data. So that is what anomaly detection. So the VAE actually performs well in the anomaly detection, and it is mostly used in medical imaging. Medical imaging, anomaly detection also done, and as well as the image reconstruction and motion and the post analysis. So in a video recognition, in object detection, or in motion detection, as I told already, so it is works nicely for the anomaly detection or change in the data. So that is what the motion and post analysis can be done easily, effectively by the VAE. And video frame prediction. So the video frame prediction is with the present frame or the current frame, the VAE can generate or predict what will be the next frame in the sequence of video frames. And of course, it is used to predict the industrial defects, like a leakage in the boiler from the images, right? So where and all we can have a kind of detection of the change in the data or anomaly detection. So the VAE is actually work nicely. So these are all some. Can someone is actually unmuted? I think. Can you please mute? Thank you. So that is what the some use cases of VAE in image recognition and analysis, and of course video recognition analysis. Some practical applications. So I already told you, right? So it can generate music and audio. I think you know the popular websites are generating the music. I think Suno is one application website offering we can generate the video, synthetic audio by giving the prompts, or we can give minimal prompt. It can generate its own music. so composes the music, and it created image generation. But the drawback in VAE is actually it is not generating the crispy images because it uses the latent space, right? So with that, it is not generating the images as crispy as GAN. It is the images can be blurry, slightly blurry in VAE, and it is works nicely for the prediction of understanding the gene patterns and the anomaly detection. So identifying the unusual change in the data. So these are some popular, widely used VAE in these areas. So we discussed two models. One is GAN, second one is VAE. And so let's see some tools. So the tools are there is no proper software bundle for VAE, but we are having some what you can say frameworks by using TensorFlow, and Keras is actually there in the TensorFlow. So it can provides API for implementing the variational autoencoders depending upon the layers. You can customize the layers, how many layers you needed, how many masking needed, convolution. So all these things we can add it. And even PyTorch also provides a necessary component for implementing the VAE. There is no proper tool, software for VAE like GAN. GAN, we are having number of tools we are having. For VAE, there is no proper tool, but we have to implement by using the framework or library, which is given with TensorFlow, Keras, and the PyTorch. So two models we discussed as of now. So getting to the third model, which is the autoregressive model. So this is the most widely used model in the text generation. Maybe in the chat GPT or in any text generation, this autoregressive model is actually used. So regression, you know it very well. So we are generating the data based on the probability. That is what regression. And we can it is works nicely for the time series data. So video or audio or those time series data is suitable for this autoregression model works nicely for this time series data. So autoregression uses the observation from the previous time steps as an input, and which is used with the regression equation. So which is used to predict the value at the next time step. That's what the autoregression. So it is very accurate in forecasting the range of time series problems like weather forecasting, temperature forecasting, rain forecasting. So like this in video and the audio time series data, we can predict what will be the next frame or next data in a video and audio. So in autoregression model, the output feature data point is expressed in as a linear combination of the past data points, which means time t1, time t2, time t3. We can predict the t4th time what will be the data, image or in image or audio, or sorry, video or audio. And in image and video domains, the autoregressive models performs pixel by pixel or patch by patch or frame by frame dependencies. So the next frame is depends on the previous frame, right? So that is what the dependence is. So the pixel to pixel and patch by patch. Patch means a group of pixels or frame by frame in a video. So it also designed for the spatial dependencies and as well as the temporal dependencies. Spatial means images and temporal means video. It generates high quality sequences even by the frame prediction technique. So a autoregressive model generates the pixels sequentially, so it predicts the next pixel based on the previous pixel. So that is what the autoregressive model works, and so that is what it's working like that. So you can see the autoregressive models can be implemented by the neural networks, recurrent or convolution, or sometimes transformer decoders also used for implementing the AR models or the autoregressive models. So these are some architecture which is given by the various ways. One is autoregressive for image modeling. So image in the sense pixel by pixel or patch by patch. That is what image model. Pixel CNN especially for the images. Pixel RNN is especially for the images. It applies the CNN and RNN respectively. Recurrent neural network. And the last one is autoregressive vision transformer. So vision transformer is the transformer model which can be applied to the autoregressive model, which can generate the text as well as images as a patch of token, a series of tokens. IGPT is nothing but image GPT, generative pre-trained for images. So vision transformer autoregressive models are actually in GPT and as well as in Gemini, the autoregressive vision transformers is actually used. So these are all some architecture. So let's see this diagram, which is saying how the autoregressive model works. So this is the architecture given by the Pixel CNN. So Pixel CNN is architecture for images where you can supply your input data. Masking is applied. Several layers are there. Some layers may be masked, and the output is generated, and it is given by the softmax. So the input and the several layers of the CNN, some layers are masked. So it depends on the method you are applying, and we can get the generated output, especially for the images. So that is what the architecture of the autoregressive model. And it is also the autoregressive model for video also it is given. Very simple. So all the image-based autoregressive, not only GenAI models can be converted to the video by temporal data. So in image, we are having the spatial data, and while converting the algorithm to the video, so we can add the temporal feature. Temporal means frame by frame. Each frame is one image, right? So temporal data. So that is what the video modeling is actually extended from the image autoregressive model by adding the temporal sequence or the frames. So they are popular or convolution long short-term memory autoregressive model. One example for the video, and the video GPT or video transformer. So video GPT is generating the video, and video transformers is another architecture for generating the video in autoregressive models. So that is what these are all architectures for the images, and these are all the architectures for the videos. And coming to the applications of autoregressive model, as I said, it is worked nicely for pixel to pixel, image to image, frame to frame. So it is work for all kinds of anomaly detection in the images and videos. If there is any abnormal change in the image, like object detection or motion detection, and video action detection, event recognition in the video. So all kinds of abnormalities in the image and video is nicely handled by the autoregressive model, and also it is giving the GPT is actually powered by the autoregressive transformer models. And of course, image classification, face recognition, all the pattern recognition, object detection, segmentation properly handled by the autoregressive model. And autoregressive model also supports the multimodal recognition. So multimodal recognition means if you supply a video, you can that is what is given over here. So video captioning. So from the video, it is going to give the caption, generate the text from the video, from the audio to video, and identify the objects in the video, and identify what is there in the video. So like this, it is giving the multiple modalities from the input video. That's what multimodal recognition. For analyzing the video, autoregressive models are best models. Anomaly detection and multiple recognition and all kinds of image recognition, classification, pattern recognition, object recognition detection. So autoregressive models works nicely. So these are all some tools for autoregressive model. And here the pixel CNN, pixel RNN for images. Image GPT is iGPT from the OpenAI for generating the images. Masked GAT, so masked convolution neural networks, which is generating the images from the Google. So the first three are generating the images. So the pixel CNN, RNN, iGPT, and masked GAT are models for generating the images. The VPN VVIT, that is video vision transformer. That is what VVIT. So it is by the Google, and the VPN from the DeepMind. So DeepMind is the organization for various GenAI models. So this VPN and VVT are for video generation from DeepMind and Google respectively. And this WaveNet and sample RNN for generating audio, that is generating the artificial music or sounds. So that is done by the WaveNet and sample RNN are the models, are tools actually. WaveNet from the DeepMind. So DeepMind given this WaveNet, And TensorFlow, PyTorch is original implementation. They given the sample RNN. So these two are for audio. So first three is images. These two are for video, and these two are for audio. And the last one, GPT, is, you know it very well, generative pre-trained model. It is OpenAI's tool for generating multi-modalities, audio, video, text, image, all kinds of things can generate. So that is what the some tools for the autoregressive models. I think let's move on to next model, which is a diffusion model. So diffusion models are models which can create high reality or high quality images and videos by gradually denoising the random noise. What happens is here is we are taking the image, we're gradually adding a noise. A Gaussian noise is gradually added. So at one step, the image is full of noise, and in the next step, we are trying to reduce or remove the noise, or denoise the images and reconstruct the original image. So that is what actual working of diffusion model. So adding noise to the data, and from the corrupted data, or not corrupted, the noise from the noised data, so we'll be reconstructing the original image or closer to the original. That is what the diffusion model actually working. So the diffusion model is gradually adding the noise to the data, and then it learns how it is happening, and then reverse the noise process, and hence we are getting the newly generated image or data. So it is systematically destroying the data by adding the noise and then reversing the destructive process. So that is what actually a diffusion model. Actually, it is works better than the GAN and VAEs for in terms of the quality and stability. So let's see this example, you will understand easily. Yeah. So this is the original image. So gradually adding Gaussian noise, and finally this is the output. This is the output. So from this destroyed image, gradually denoising the image, and we will be generating the new image which is closer to the original. That is what actually diffusion model is working. So it is having two entities, forward process and reverse process. In forward process, diffusion is happening, adding the noise to adding the Gaussian noise. And then second step, diffusion reverse process, we are denoising or reconstructing from the denoised image. Right. So, or we can call this a generation. So from the diagram, you can see the original image is actually supplied to the diffusion model. It's gradually adding the noise over there. So you can see this one noisy image. So this diffusion model has a knowledge about this, how it studies the pattern, how these things would be there in from the knowledge base, it can regenerate from the noisy image. This is what the newly generated image, which is closer to the original but not original. It's a synthetic data. Okay. So this is how the diffusion model is actually working. For generating the noises to the image, Markov chain is actually used. So Markov chain is having used. Remember the present data and the previous data. It is a chain of function. So this Markov chain is actually gradually adding the noise, and it knows where it is added and what it is. So all the information the Markov chain is actually having. So after many steps, so the image becomes noisier one. So we are not able to see what it is, what is there in the image. And in the second process, in generative process or in the denoising process, so the reverse Markov chain is actually applied from the Markov chain. It knows where and all we are having the connection. So from that connection, it is a reverse transition is actually applied. Reverse transition property is actually applied, and hence it is generating or creating the reconstructing the image from the noised image, which is actually a new one. So generally the unit is actually used for denoising the image, and with the reverse Markov chain, it is going to regenerate or denoise or generate the image. So simply I can say the diffusion model is having two components. Diffusion is adding the noise, and reverse process is going to be called as a generation or denoising the image. And so these are all some types or variations in the diffusion model, different implementations. So the first one is DDPM, that is a denoising diffusion probabilistic model. So here, this is what the one which we saw now. So we are having two Markov chain. One is for adding the noise, and second chain is for denoising the image. So DDPMs are commonly used to eliminate noise from the visual data, real world application. And next one is SGM, score-based generative model. So here score functions are used. So with the score functions, the parameters are estimated, are adjusted. So with the new parameters, so the denoising can be done. So that's what score-based generative model, SGMs. And the last one is SDE, stochastic differential equation. So where we are having many number of diffusions, or many number of diffusion steps are there. So infinite, for example, I can say infinite number of diffusion steps are applied exhaustively. So with that, we'll be noising the image and reconstructing the image. That's what called a stochastic differential equation. So these DTPM, SGM, or SD are some popular variations or types in the diffusion models. So these are all some use cases. I mean, in recognition analysis, denoising. So as the implementation, you know that adding the noise, removing the noise. So it is worked nicely for the denoising based recognition, and it is used in helps in scene reconstruction and completing this scene which is incomplete, and text to video simulation and training the data, occlusion removal. So in an object, in a scene, there might be some hidden object might be there, so that can be successfully removed, and we can get the full image and proper image. That is occlusion removal. And of course, hyper-realistic synthetic data sets for search purposes or training. So these are some recognition analysis by the diffusion model. So diffusion model, we are having noising and denoising. That is what the basic. And these are some tools for diffusion, and DAL-E and DAL-E2 and E3, SORA. SORA is not available in India. And stable diffusion from stable, Midjourney. So these are all some things. So we can explore some. Let's see. I think you can see my web page, where you can see the. So this is the image generated by the DAL-E, DAL-E2. So hyper realistic images, and from DAL-E 3 is generating this image actually, and SORA. I think you can see this video. So visible. So this is actually purely generated video by the diffusion model called SORA. And you can see this one, a lady walking on street, I mean a city street, a Tokyo city street, which is purely artificially generated video by the SORA again. And this also from the, so the thing is, you have to give the prompt in such a way. So from its knowledge base, it is going to be generated the hyper realistic videos. This is not actually true. So this is a generated video. See, you can see the chair is actually floating. So you can see this diffusion image given by the Stable. So Stable is organization which is they're working in a diffusion based GenAI model, which can generate the hyper realistic images of the cow and as well as dog. So like this, Midjourney is the company. So this is the image created by the Midjourney by the prompt. So like this, so is my screen is visible?
Yes, sir, it's visible, sir.
Yeah. Actually, from switching from website to the so these are some tools available for diffusion model, whether DAL-E, SORA, Stable Diffusion, and Midjourney. You can try later. DAL-E and DAL-E2 and E3 are two versions available in India, and rest is ready to come to India. So you can try the hyperrealistic images can be generated by these tools. So that is the diffusion model. And moving on to the next model, flow-based model. So here, the flow-based models are a kind of simple tractable probability distribution into actually we are converting a simple to the complex data. That is what actually flow-based model. So the flow-based model transforms the simple tractable probability distribution into complex multimodal distribution. So using a series of invertible and differential transformations, so purely mathematical transformations by functions called invertible and differential transformations. So of course, we're not going to discuss the mathematics here. And it transforms a simple distribution into complex distribution through the reversible function. So that's what called as invertible function. So I think you can see all these models are applying some, taking some mathematical statistical function, applying on the data and generating a compressed form. From the compressed form, it is going to be regenerating a reconstructing. So that is what actually happening. So here also in flow-based model, so we are converting data to the invertible complex distribution. So from the complex distribution, we are trying to reconstruct the as closer to the as original data. So that is what flow-based model. And let's see. So this is how, yeah, so it's similar to encoder decoder scenario where X is your input data, the flow function, invertible flow function, which can convert your data in a latent space. That is called a latent space. So from the latent space, we apply the inverse function of this one flow function. So this inverse function is generating the data from latent space to the newly generated data. Just this X dash is not as X, but it is closer to X. So since it is a generated image, it is closer to the original, but not original. And the latent space, the flow-based model is having several layers like coupling layers, affine transformation, squeezing function, and splitting function. So again, it is going to be repeated. So several layers are there inside the flow and inverse function. Very simple. If you take the data, convert to one form and invert it, we can generate a new image or new data. So here it's architecture. This diagram is actually given by Gemini AI. We are having a data and as well as is that X is going to be your data. Z is actually latent space. So the converted data. That's what the compressed data is it. And we are having several layers are stacked over here. So I think you couldn't see the layer. I'll read the layers. So the layers are like coupling layer, invertible one by one layer, and convolution layer, and invert. Yeah, you can see over here. So splitting layers, permutation, invertible one by one convolution layer, coupling layer by the affine transformations. So these are all the several layers which is used to convert your data to latent information. So latent space. So you are having your original data by the several layers. You are converting all data to the latent variable or converting your X into Z. Z is called as latent variable, which we can represent data in a latent space. So again, from the stacked reverse function, reversible invertible function, from this latent variable, we are able to reconstruct the image, reconstruct the data. So this is forward, this is reverse. So this is how, or else you can say this is training and this is going to be called as generation. So the left side is training and right side is generation. So this is how the flow-based model working by using invertible function and the transformation function. So with that, the flow-based model architecture is over. And these are some implementations of the types or variations in the flow-based model. The first one is the non-linear NACE, the non-linear independent component estimation. So it is the first of its kind, first major flow-based model. It uses the coupling layers and as well as the additive coupling layers. And the second one is real MVP, so real valued non-volume preserving network. So it is introduced the affine coupling layers, scale invariant and shift transform. So these two layers are introduced, added. It's very simple. If you add, you can customize your layer and add your layer. If it is generated the proper output, we can take that. So that is what actually they tried. And third one is GLOW. So GLOW is actually generative flow with invertible one-by-one convolution. I think you can see in the diagram I told, right? So one-by-one convolution. So it add invertible one-by-one convolution layer to the transformation function. That's it. So that's what called as GLOW. And the fourth one is NSF, neural spline flows. So the function used for transformation is spline function or spline transformation. So with the spline transformation function, we are converting the data into latent space. So based on the function used for transformation, the type actually varies. So the last one is a continuous normalizing flow, CNF. So here the ordinary differential equations are used for transforming your data X to the latent space. So that transformation only plays a role, and layers also plays a role in defining the different implementations of the flow-based model. So the NAC, real MVP, GLOW, and NSF and CNF are the some variations or implementations of the flow-based model. So these are all some applications of flow-based model. It almost image and video similar application except the frame prediction. So image and video can be generated, and super resolution image and video can be generated, and it can translate the image to one form to other form, and anomaly detection done in both image and video, and it also compress the image and video, and it also helps in image editing. So almost all the applications are same in both image and video except the frame prediction and the editing and translation. So rest of all the applications are same for image and video in a flow based. So flow based model helps in generation of images and video, super resolution images, creating super resolution images and video, and anomaly detection in both images and video, and as well as the compression. So these are all some applications where flow based model can work. And here's some tools for flow-based models. So the NICE actually the implementation just now we saw, right? So this NICE is actually implementation. So given by Tiano, and GLOW also an implementation, one-by-one convolution by the DeepMind, and NSF is also by the Pyro. But that is Pyro is a framework which is given by the Uber AI Labs. They actually implemented. They tried and given this neurospline flows. So like this, we as a researchers, we also try some different layers or different combinations or different things so that we can implement a new way of implementing the deep learning frameworks. And the fourth one is free form Jacobian reversible. So this Jacobian is actually a function for used for transformation, Jacobian transformation in multivariate mathematics. And it is given by the PyTorch is actually, and SR flow is something but super resolution flow. So this flow is actually given again by the PyTorch. So the PyTorch is actually they given this implementation to open to everyone. So no companies claim that that's their implementation. So it's open to everyone. So these are all some tools for flow-based model: NIC, GLOW, NSF, JORD, Jacobian based, and SR flow, super resolution flow. By the name itself, we can know that which application, which tool is useful for the which kind of application. For example, SR flow is used to generate the high resolution images and video, and the NIC is actually works nicely for the images, and GLOW is actually used for both image as well as the video. So like this, we can use the tools for the respective domains. That is what about this flow-based model. I think we discussed, I think, 5 models, right? So let's go on to the, yeah, I think we discussed 5 models. So these are all some models I told in the beginning: GANs, VAE, autoregression models, diffusion models, flow-based models. So 5 models so far we discussed. And the last one is a hybrid models. So actually, hybrid meant for combining two models. But here I combined generative models with the discriminative models. As a researchers, you also try the hybrid GenAI models itself, hybriding VAE and GAN, hybriding autoregressive and GAN, hybriding diffusion model and the flow model. But the reason should be convincing. So that is in that way you have to hybrid. So let us see the last type in the GenAI model. That is hybrid. Yeah. So coming to hybrid generative discriminative model. So so far we were discussed about the five models in generative models, starting from GAN, generative adversarial network, and second one is VAE, variational autoencoders, and the third one is diffusion, autoregression, and as well as the last one, flow-based model. So these five models can be their components can be leveraged. But here, what I tried is hybrid generative and discriminative model. So generative model, we know it very well. Generative models are the machine learning models which can learn the data, understand the pattern, and generate the images, videos, text as closer to the reality. So that is what generative model. So coming to discriminative models. So discriminative models are it is a kind of mapping. So if these features are available, it belongs to the class C or class B or class C. If these features are available, this belongs to the particular group. So like this, it is having a kind of mapping. So that is what the discriminative model. So let's see what is there actually the definition. So generative models learn the data by the joint probability. So P of X comma Y. So if X is there, what is the Y? So what is the relationship between X and Y? So that is what joint distribution or joint probability distribution. So each of the data is actually related to other with the P of X comma Y. So with that, we can generate, with that, the generative model can generate a new data, that is VAE, GANs, diffusion models, flow-based models, regression models. So these models actually learn the data's joint probability, learns the connections between the data, and it can generate the new data or synthetic data. That is what the generative model. Or simply I can say generative model works on joint probability, whereas the discriminative model works on the conditional probability. Okay, if these are the features are available, I can say that is belong to class A, otherwise class B. So like this classification, a kind of classification. So discriminative models learn the conditional probability. So P of X given Y, Y is already happened, and what is the probability of X? That is what P of X given Y. It's a kind of a direct mapping from input to the classes or input to the labels. So the popular, I think you know all the classification models starting from SVM, PCA, logistic regression, even transformer models, even the convolution networks. So all these neural networks, transformers, regression models for classification, SVMs, PCA, all these models are machine learning models. Based on the conditional probability, it is deciding which class it is, or it is deciding what is the output. So it is not generating the images, it is not generating the text or images, or video or audio, but it is giving the result, giving the classes. So that is what the generative and the discriminative model. So here the hybrid model is actually combining both generative and discriminative components to leverage the complementary strengths of each. For example, generative model work nicely for in one domain, and even generative model can guide the discriminative model, and discriminative model can also help in the generative model. So like this, the strength of the each model can be leveraged for the effective output. So these models combine both generative discriminative models, and these components to leverage their complementary strength. And yeah, so here I given some examples in hybrid generative discriminative model. The first approach is generative model and discriminative joint. So jointly, so generative discriminative joint models. So both will be there in the model, and each of the strength can be used in generation of the output. For example, any GenAI models plus any classifier. GenAI models, you can take GAN or VAE or any model plus any classifier, CNN or PCA or anything. And the second approach is generative models which supports discriminative learning. So in discriminative learning, actually discriminative models are learning the data. For example, in CNN learns the data, right? So for that learning, the generative models are helping, are supporting the discriminative learning. So that is what. So GAN based CNN. So GAN helping the CNN effectively read the data or train the data. That is what the second approach. And third approach is discriminative models with the generative regularization. I think you all know about what is regularization. Regularization is used to adjust the parameters or reduce the errors or tune the output. That is what regularization actually. Reducing the errors or adjusting the parameters, changing the output of the model. Based on the regularization parameter, it can change the output. So that regularization can be done by the generative models. So this regularization used in discriminative models. So that regularization component will be any generative models. For example, GAN is one model which is act as a regularization for the discriminative models. For example, in CNN, GAN is acting as a regularization model. Or in any classifier, GAN is acting as a regularization in that classification models. So like this, we can combine generative and discriminative models. It is not. It is my view actually. You can try any kind of hybridization of these two models. So it's my approach. So I try to say these models are possible, and many more may be available. So let's see some examples of the combination or hybridization. In the first example, I told you, right, GenAI model and the classification. So I took VAE and the classifier. So you can see over here. So VAE and the classifier. And any classifier, it could be any classifier. So it can be used for joint learning, and accuracy is actually improved with the classification, with the VAE. And second one is GAN and CNN. So where GAN is GAN and CNN is works together, which extracts the future nicely, and high quality of data augmentation can be done. So like this, we can combine any two models. So see over here, so vision transformers and the VAE, vision transformers and the GAN model, and diffusion classifier guidance model. So for classification, we are applying diffusion, and the transformer model with the diffusion. So like this, we can combine flow models in the CNN, and GAN with the for classification, GAN is acting as an auxiliary tool. So like this, we can combine any of this GAN model, hybrid, generative models with the discriminative model. So use cases. So based on the use cases, you can legibly use those models together for effective output generation. So that is what some examples for people who are doing research in deep learning, and take this area where you can combine different generative discriminative models, depends on their area of research. They can try, and they may try this area. So that is what about the hybrid of generative discriminative models. And of course, I think I finished all the models, starting from VAE, GAN, diffusion, the autoregression flow models, and ended with the hybrid generative discriminative model. So I think I completed 6 models now. And let's see how these models are help in image recognition and video recognition analysis. So that is what the next one. So by for a generative model for image recognition, so GenAI models are learn the underlying patterns of a data, image data, and generate new samples, and sometimes reconstruct the images. And also it provides a deeper representation learning, so self-learning. So in image recognition, GenAI models are used to learn rich latent feature. Latent feature is hidden features in the data, and it also improves the robustness of the model and enhances the classification accuracy, which is efficiently handling the missing data or corrupted data, and supports anomaly detection. So these are some image recognition where generative models can help or work nicely. So like this, I can say for video also. So instead of saying as a slide, let me see this table where we can. So this table is actually saying about the generative models for image recognition along with the limitations. So the first model is GAN. So GAN is actually a generative adversarial network. So we are having generator and the discriminator, a kind of adversarial game. That is what the technique used by GAN. So it is used in the image synthesis, super resolution images, style transfer, image to image translation, face recognition, face enhancement, and even medical image processing like medical image segmentation. So those are all the areas where GAN is actually working. So the limitation of GAN is of course it is producing a nice hyper high resolution images, but it produces some limited variety. So it is not generating as much as of output. So it is having some limitation in the and training is unstable. So as the model is complex, the training is unstable. And also it requires a large data set. So it needs a huge amount of data set for training. So that is some limitation of the GAN. But it produces the high quality, hyper realistic images. That is what the GAN for image recognition. And coming to second model, VAE. So we are having encoder and the decoder. Encoder is encoding the input in a latent space, right? Or dimensional detection and putting in a latent space or latent vectors, where decoder is going to be reconstructing from the latent space to the original. That is what actually the VAE working for the application area. So feature extraction, anomaly detection, medical image segmentation, latent interpolation are some areas where the VAE work effectively. But the problem in the VAE is since it is working from the latent space, it may generate some blurry images. So the images are not sharper, but it works nicely for the abnormal activities in the images and as well as the videos. That is what the anomaly detection. That is what. So due to this latent space, it generates the blurry images as well as the less realistic images. That is a problem in the VAE. The third model is the autoregressive model. So autoregressive model, it is having pixel to pixel, patch to patch, or frame to frame kind of thing. So it works efficiently for the text synthesis, image completion, pixel level analysis, and unsupervised representation learning. And the problem in the autoregressive model is it's very slow. So due to pixel, patch to patch, or image to image processing, so it is very slow, and it needs a high computational tax. Whereas the previous methods are having some dimensionally reduced data will be there that with the figure they can play. But whereas these auto-regression models are actually doing with the image to image or the pixel to pixel, frame to frame. So in that, it need high computational cost and as well as slow, very slow in generation. That is a drawback in the regression model. The next model is diffusion model. So diffusion model is, remember this, adding the noise and denoising. Denoising, we can reconstruct the image. So with the scores, so that is what the diffusion model. So there we are having generating the high quality super resolution images or image restoration or image restoration, synthetic data set creation. So these are some areas already been discussed where we can generate high quality images. That is what the diffusion model is actually doing. But the problem in the diffusion model is slow sampling. So because it has to create the high quality, hyper realistic, super resolution images, it needs a slow sampling. It needs a time, right? So it needs a time, and of course, it needs a high computation GPUs. So it is very hard to tune the noise schedules. So adding the noise, removing the noise is going to be a high computation with the GPU, and also it is slow in sampling. So that's a problem with the diffusion. But it is super resolution images can be done effectively by the diffusion models. The autoregression can generate the pixel to pixel. That is what the autoregression. So 4 models done. 5th model is actually flow-based model. So flow-based model, we are having invertible transformation function. So we are having a function, and the function can be inverted, which can be used for generating a new images or output. So here the application areas are image to and video generation, super resolution, compression, and even editing also possible with the flow-based model. But the problem in the flow-based model is, so we are having the inversion, right? So we are having some limited model design for inversion. Function is less, but it is not working for the high the scale, I mean, if the image size is too high, so it is difficult to work. So hard to scale the high resolution images. So high resolution or huge images cannot be done easily with the flow based model, and the lower accurate comparing to the rest of the models. So where and all you need a generation, compression, and we can anomaly detection. We can use the four-burst model, but the problem is inversion function is limited, and it is scaling to high resolution is not working nicely, and low accurate than the other models. So out of the 5 models, this was somewhat low resolution when compared to other models. And coming to the 6th model for images, hybrid generative discriminative models. So it is the technique and the application and limitation is actually depends on what kind of generative and discriminative model you're choosing. So each model is having its own limitation. So again, the technique is based on the which generative discriminative model you're choosing, and as well as the limitation also based on the which model you are choosing. So this is how the generative models can be given in a single table for image recognition. And the for images, the same thing. So all the images will be converted to the video by adding the temporal parameter, temporal thing. So that's what. Let's see that. So generative model for AD recognitions, of course, applications are same. So instead of image, we'll be talking about video. That's what the models. So first model is GAN model for video recognition. So GAN model, we know that adversarial discriminator generator model, we know it very well. So deep video synthesis, deep fake video synthesis. So it's a high demand in nowadays. And video to video translation, video super resolution, and motion transfer and reenactment and video generation. So these are all some applications of the video GAN in video recognition and generation. The problem with the GAN is, what is the problem? So there it is needed high computation, right? So here also temporal inconsistency is a problem. So flickering may happen in the videos due to the inconsistency, and it is training the image to video is in GAN is very difficult or time consuming or hard, and sometimes it may collapse in dynamic scenes. So that is problem with the GAN. And coming to VAE, so encoder decoder model, so video frame interpolation, anomaly detection, compression, motion aware representation, action recognition are some applications of the VAE in video recognition. But the problem with the VAE is it can generate the blurry images, right? In image. So here also it can generate some blurred video frames. So limited in motion sequences, less realistic than the other models. So I'll already told you, right? So the VAE can generate the blurry images. So here also it generates the blurry video frame. That's a major limitation in the VAE. The third model is auto-regression model. So where we are having the converting the images to video, whether it's spatial image to the temporal video. That is what actually in spatial video to video, I mean frame to frame or pixel to pixel. In temporal, frame to frame, temporal data is actually added. So video generation, motion prediction, feature frame forecasting are some examples or applications of the autoregressive model. But the problem is it's very slow because the video is generated frame by frame, pixel by pixel, or patch by patch. It is very slow in generation. It is difficult to model for long-term dynamics. That is the thing. Coming to diffusion model is noising and denoising. So extending the image into video. That's it. Adding the temporal extension is applied to the images. So high quality video diffusion, impeding, editing, frame per second upscaling, object removal, motion synthesis are some applications of the diffusion models. Here also same thing, very slow in sampling. So same problem in the images here also same. So multi-step per frame is a problem. So very high computational cost in diffusion model. So temporal consistency also a problem here. So it may flicker. So if you generate a video by the diffusion model, it may flicker due to the inconsistency because of the temporal consistency it's a challenging thing in the diffusion model. And the last model is a flow-based model. So inversion to the spatial temporal transformation, video anomaly detection, action recognition, video compression. So these are all some applications of the flow-based modeling. So here the problem is limited expressiveness due to the invertible. So invertible function is limited, similar to image. Image also we are having the same problem. Limited invertible function. So it is poor reality than the existing the other generative models. So hard to scale for long videos. So for long videos, it is not work nicely. That's what the problem. So these are all the problems and limitations in the applications of the generative model for the video recognition. Hence, I covered the generative model for video recognition. And though we are having all these things, we are having some limitations already we discussed. Let's see some challenges in the generative models. For example, the first and foremost is computational cost. So I need a GPU or more GPU time for generating frame by frame, pixel by pixel, invertible function, encoding, decoding. So all this transformation is need a high computational power. So on memory also. That's the first problem and a challenge in the generative model. And data biases. Some data generative models having knowingly, unknowingly, it is having some bias with respect to the data. So if you are converting a data from one domain to other domain, so we are having the problem of domain shift. So we are ultimately it may results bad quality output. That is one challenge. And next challenge is evaluation metric. There is no fixed evaluation technique for evaluating the accuracy of the generative models thing. So again, it is going to be specific to the particular task. So it may generate a video or image or text, synthetic data. So it depends on the use cases. Again, the metrics, evaluation metrics varies. So again, that's a problem. That is a challenge. And hallucination. So that's a big issue in the generative model output, where it can generate hyper images or videos or whatever it is. It is not actually true. So that's a problem. Hyper hallucination. So people who are interested in doing research in generative models, we can concentrate in the hallucination problem and as well as the evaluation metrics. And the next challenge is deployment. So if you wanted to deploy your generative models in standalone computers, doesn't matter. But mobiles and the small devices, it is a challenge. Still, it's a challenge. So people working in want to work in deep learning or generative models. So you can concentrate this area too for customizing the generative application for the mobile devices or low computing devices. So that also a challenge. So these are some challenges in generative model, GenAI models implementations. Yeah, that's it. I think I covered all the things. So right from the types of introduction, types of all the GenAI models, and the applications of the GenAI model, and as well as generative model for image and video recognition, and that's it. So I did a small research for today's presentation, how the GenAI models are there, the history, and everything. I think most widely used GenAI models are ChatGPT and as well as the deepfake, even Gemini, and try to go through what are the architectural models used by ChatGPT and Gemini, even deepfake, DeepSeek. I think in ChatGPT they're using transformer models, and even in Gemini they're using Gemini actually from the they're using a transformer, I think transformer auto regression models. So that is what they're actually doing. So the ChatGPT and as well as the Gemini models are multimodal GenAI models for generating all kinds of modality in text, image, video, audio, etc., are there. So I think I covered all the things which I planned. Thanks for the people who have spent the time at this evening. And after all this, we are having a small quiz. So let's check out whether what's your understanding about today's session. Not going to be for evaluation, but how about a simple thing? What all things we gone through past 1.5 2 hours? So let's check out your memory. So let's float the quiz now.
They can share the option in the chat box, no, sir?
Yeah, of course, sir.
Okay, okay, sir.
I just wanted to share this information to the people who are in the. These are all, so you can focus these challenges. So if you wanted to do research, these are also the first areas in GenAI models, especially, where you can focus your research for where you can find your novelty over here. Evaluation of generative GenAI models and hallucination, how to avoid this problem, hallucination problem, and deployment of the GenAI models in the low computing devices. So these are all the areas where you can focus to do your research. If you're having any queries, you can post in chat, or else you can unmute.
Participants are encouraged to post their questions in the Zoom chat box, or you can unmute and ask the question to the resource person. Participants, any clarification to ask to the resource person? Either you can raise a question unmuting your mic, or you can use the chat box to put your message. Any queries, participants?
No worry, bro, sir.
Okay, sir. Okay, sir.
Uh,
Okay, sir. We'll wind up. Thank you very much, sir, for delivering.
Sir, so one
Yes,
more
sir.
thing, sir.
Yes, sir.
I have a small quiz over there. We'll float the
Okay.
quiz. It's a 20 questions roughly. It's a simple question
Sure,
based
sir.
on our
Sure, sir.
presentation.
Okay.
Let's have this quiz and then we'll wind up, sir.
Fine, sir. Fine.
You can scan this QR code, or else you can visit joinmequiz.com and give this pin.
Sir, we will do one thing, sir. Share the QR code in the group, sir. Why? Because if they come out of the
Yeah.
screen, means the Zoom will get cut off for to them.
Okay. Then. You save the image. So where should I share, sir? In a group.
You send it to me privately, sir, in the WhatsApp, or else you share to Revati, ma'am. We'll share it in the common group.
I'll share it to Ram.
Yes, sir. Yes, sir. Participants, you will share the QR code for the quiz in the common group which we have. You can make a try over it. Thank you very much, sir, for delivering such a compelling and thought-provoking session. Your expertise and clarity have indeed broadened our understanding. To formally express our gratitude, I invite Dr. B. Hidayat Nisa, Assistant Professor, to present the vote of thanks and acknowledge everyone's contribution to today's event. Ma'am, please take over, ma'am.
Thank you, sir. A very good evening to one and all.
It is indeed a great honor and privilege to deliver a vote of thanks on this expert session. I extend my sincere gratitude to our management for their unwavering support and commitment to fostering academic excellence. Their vision and encouragement make it possible for us to organize impactful academic events. I express my respectful thanks to our director for her consistent guidance, leadership, and motivation, which inspire us to pursue and host meaningful scholarly engagements. A heartfelt appreciation also goes to our head of the department for providing the necessary actions, direction, coordination, and encouragement for the successful conduct of this program. I would like to place on record our profound gratitude to our esteemed resource person, Dr. M. Suresh Anand, Assistant Professor, Department of Computing Technology, SRM Institute of Science and Technology. Sir, your insightful presentation on generative models for image and video recognition and analysis shed light on emerging techniques and future advancements, making the session highly valuable and intellectually stimulating for all of us. I extend my sincere thanks to all our faculty members for their cooperation and support throughout the planning and execution of this event. Finally, my deep appreciation goes to all the participants. Your active engagement and enthusiasm played a key role in making this session meaningful and successful. Once again, I express my sincere thanks to everyone for your presence and support. Thank you all.
Thank you, ma'am, for the gracious words of appreciation. With that, we conclude the day 3 session of our International FDP. We sincerely thank all the participants, the resource person, and the organizing committee for their wholehearted support. Participants, the day 3 feedback cum attendance link has been posted in the Zoom and YouTube chat box. Kindly fill it out. Participants, once again I repeated, the day 3 feedback cum attendance link has been shared in Zoom and YouTube chat box. Kindly fill it out. The response will be active till 8:30 p.m.
Shall we wind up, sir?
Suresh and sir, you can leave, sir.
Yeah, thank you.
We'll wait
Thank
for
you.
5 minutes and we'll also close.
Thank you.
Okay, sir. Thank you, sir. Participants, the feedback link is available in the chat box in Zoom and as well as in YouTube. Kindly make use of it. Participants, once again repeated, the feedback come attendance link is shared in chat boxes of YouTube and as well as in Zoom. Please kindly fill it up. Veera, sir.
Sir, shall we end, sir?
2 minutes, sir.
Okay, sir.
Okay. Veera, sir, you can end the session, sir.
Okay, sir. Okay, sir.
Thank you, sir. Thank you, sir.
Okay, thank you, sir. Thank you
Yeah,
very
thank you,
much.
sir.
Okay, sir.